Hey everyone, want to welcome you to the next Math for the Impatient. I'm here with Stan Kladko, the CTO and co-founder of SKALE. Hey Stan. So we were talking about ZK. This is part of the ZK miniseries. What I'm particularly excited about is to learn more and go a little bit deeper. So we did a really kind of high-level view analogy of ZK. Today we're gonna go into sort of the first steps of ZK, and it's an idea called arithmetization, which I have no idea if I said that correctly, but Stan, tell us a little bit about that.
Yeah, so as you guys remember, last time we just had the first part of our series, which was just introduction into ZK, and we had this example of the king and the treasurer, and basically the king wanted to do some computation, and the treasurer was doing the actual computation for the king. But the king wanted to verify the treasurer because the king didn't trust the treasurer. So this is a very typical thing in ZK where someone computes something complex, and then the king or like the verifier wants to verify this complex computation. Typically, the prover could be like super powerful computer, and the verifier can be as slow as blockchain. So last time we discussed like the high level picture. And today we're going actually go a little deeper into the actual steps of how ZK works. But I strongly recommend, if you didn't see the first part of our series, to stop and first to see the first part, because we're gonna go a little further today using this essentially the same example as we used during the previous session. For those of you that actually did watch our previous section number 1, let me recap what we had. We had the king. The king wanted to compute how much money he spent during a particular year, and the king had this long list, was passing the list to the treasurer. The treasurer was doing the computation. But then, as you remember from our previous series, the king was using this trick. As you remember, the trick was to actually to tweak the numbers a little bit and embed into each number the fact that it's divisible by 13. And then the king could actually verify it, and if the thief would actually, the treasurer would be dishonest, then the king would be able to find this out. So what is basic about computation, about verification of computation? You pass something into someone, but you also embed this hidden law inside. So when this person comes back to you with the result, you can check the hidden law, and if it's broken, then you know that this other party was not correct. Now, let me talk a little bit about the 3 laws. So as you remember, there was this principle of sampling, that if you want to verify some computation, you want to sample it. There was this principle of hidden law, that you embed into the computation the hidden, kind of something hidden that you can actually later verify. There was the principle of divisibility. Remember, we talked about modular arithmetics. We divided by 13, all of this stuff. And then there was this principle of survival, where the hidden law was actually surviving through all of these multiplications and divisions. It turns out that these 4 principles are exactly satisfied with ZK, in particular for a particular type of ZK that we are going to be discussing, which is called PLONK, P-L-O-N-K, another strange name. And this type of an algorithm, PLONK, is the widest used algorithm currently. It's supported by many libraries, many people use it, and it's kind of the easiest to explain. That's why we're going to be talking about PLONK. Now, again, a recap of industry terms. When we say sampling, mathematicians say Fiat-Shamir method. There is a famous computer scientist, 2 of them actually, Fiat and Shamir, that contributed lots of things to sampling. So in cryptography, all things related to sampling are called Fiat-Shamir method. The hidden law is actually called the probabilistically checkable proof system, or PCP system. So if you at a party and there's a startup in ZK and someone talks about PCP, that's actually the hidden law that we've been discussing, the PCP system. Adding and multiplying numbers, especially modular p, where p is a prime number, is called something which in mathematical terms is called Galois field algebra. And Galois, Galois is a famous French mathematician, which actually was doing all kinds of things with prime numbers and multiplication and addition of prime numbers. That's why people call everything related to the thing Galois field algebra or Galois field theory. As I mentioned, the actual hidden law is called polynomial PCP. And finally, this actual result, the thing that you pass to the king, essentially, the numbers, are called SZK proof. And in a real life, SZK proof is usually from 100 bytes to 1,000 bytes. In some cases, for instance, for ZK Starks, the proof can be a little larger, maybe several kilobytes. But for most algorithms like PLONKs or ZK Snarks, the proof size is from 100 to 1,000 bytes. So it's pretty small and can actually be posted to blockchain. So when people say we're running things to a blockchain, they're actually running this small pieces of data, these small proofs. Now, the rest of this mini series is going to talk about two fundamental steps of ZK. It turns out that every single ZK algorithm can be split into the front end and the back end. And it usually happens in life. Different people do different things. So people that do front end, they don't really know so much about the back end. And people that do the back end don't know so much about the front end. And all of these things are typically open source. The front end says that every mathematical formula and every algorithm, anything, it could be your Microsoft Word or your image manipulation. Turns out everything can actually be expressed in multiplying and adding numbers, something which is called arithmetization. And that's our topic of today. And this may actually feel strange to you, but then you can think about like the processor. We're talking now on Zoom. The CPU of Intel or Apple doesn't know about Zoom. It only knows about adding, multiplying, subtracting, dividing numbers, about the simplest mathematical operations. So everything and everything can be explained, can be expressed in terms of addition and multiplying of numbers. And that's something which is called arithmetization. We're going to discuss it today. And then if you do this arithmetization, if you move from whatever software you have to actually just multiplying and adding numbers, then once you have this representation, it turns out that any combination of additions and multiplications can be injected with a hidden law to generate a ZK proof. And we've been talking about RTOI, insecure ZK proof, but there are many secure ZK proofs. And in our mini series, we're going to focus on PLONK because that's the widely used and the easiest to explain ZK algorithm. Now, first of all, if you want to use ZK, you actually don't need to know so much about this. For the front end, to turn your software into multiplications and additions, nowadays you can use multiple frameworks. There's a framework which is called Halo 2. And that's a widely used framework. You can use that one. Typically, if you don't want a great performance, you can just use it. If you want better performance, you can manually tweak things. And then for the back end, if you want to use PLONK, it's typically done by a crypto framework, and few people actually touch the code. So most of the software engineers that actually do ZK don't really go so much into the back end. They just use it as a black box. For the front end, if you need a simple computation, you just also use the framework. If you want to tweak performance, then you go a little deeper. But the point is that you can actually use ZK now. Having the information that we are having in this mini series, you can go download Halo 2 or some other framework and start using ZK. Now, let me go into the arithmetization in more detail. And you might ask the question that, okay, the example we considered last time was very simple. The king was just adding, basically multiplying prices and adding numbers. It was all very simple formula. Can you do a more complex formula? And so let's consider the example where the king is selling wheat. The wheat is stored in containers. And so the king sells 2 large containers and 3 small containers. and the treasurer, and asks the treasurer how much the total volume is. Obviously, from the elementary school mathematics, we know that to compute the volume, we need to multiply dimensions. But in our case, we have 2 containers and 3, 2 large, 3 small. So the total volume, the total formula is 2 times x times y times z plus 3 times a times b times c. So that's a simple formula, and there are specific numbers. And as usual, the king passes this to the treasurer, and the treasurer wants to make tweak the thing. Maybe the treasurer stole the wheat, for whatever reason, the treasurer wants to provide the correct number. So then we had the trace. Remember, we had the trace the previous time. When you do the computation, you record each and every intermediate result. In this particular way, the trace is done a little differently. So you have these 4 columns. The first column is the operation, which can be either multiplication or addition. And then in this particular example, let's say you want to start. The first thing you want to do, you multiply 2 by 1645, you get 3290. Then you take 3290, you multiply it by 784, you get this number, and I think I made a mistake. You don't need this line here. Oh, you actually do. You multiply by 965, you get that number. So you have this very simple mathematical computation. Everyone can do. It's elementary math. And I'm not so good in multiplying large numbers. So what I decided, I'm going to leave this as an exercise for our viewers, just to compute this trace, to complete the trace. I did this first 3 operations. Now you need to multiply these things and then ultimately add them. So the trace is going to be longer. The first exercise for our viewers is just complete the trace. And on Friday, I'm going to complete it myself and just tweet the result. So that's the first thing. And the second thing, you might suspect that the idea of division by 13 actually works exactly in the same way here as it worked in our previous example. Essentially, you tweak each and every number. The king tweaks each and every number here to make it divisible by 13. And so the second exercise I want to leave to our viewers is just to do the same trick as the last time and show that if the thief tries to tweak the numbers, for instance, add this 1 here in front of 2, the king can also verify the computation by dividing the result by 13 and verify it's not divisible by 13. So the exercise is to take what we had the previous mini-series example, apply exactly the same thing, and show also that for this particular formula, the division by 13 trick actually works. So we not only can embed our hidden law into addition of money, but in this example, in more complex formula, when we calculate volumes and add the volumes. This I'm going to leave for the viewers, but on Friday, I'm going to do it myself and also post it on Twitter how it's actually working. But then what we got from this example, you understand, now we have this more complex formula, 2 times x times y times z and pam, which we can also use this trick to catch the thief. And we can actually do it exactly in the same way for any polynomial, any multiplication and addition of x, y, z, pam. And basically anything you could imagine from your elementary school, you can apply to any formula in your elementary school, the same trick as in the previous section. And now another interesting thing is that it's known in the mathematics that pretty much any data you can approximate this polynomial. So in a sense, anything and everything in life is a polynomial because you can imagine any number, any data set. You can take, tax table from IRS, and you can approximate this polynomial. So essentially, if you're getting to larger order polynomials, you can express any data in it, anything, any formula, which kind of concludes our session. So which basically shows that every single formula you can imagine, you can approximate as a polynomial, and for the polynomial, you can use the trick we discussed to actually catch the thief. Now, one more thing which I wanted to discuss is as a different exercise. Sometimes people represent these multiplications and additions as gates it's very common is in Stark and Starks to use this gate representation. So the representation using a trace here is a PLONK representation, something that PLONK is using. Other ZK algorithm using this particular representation, and this particular formula is A plus B times C. So the third exercise I would like to just give to our viewers, if they want, to draw the same gates for the formula that we use, 2 times x times y times z plus 3 times a times b times c. So this is a gate representation, more graphical. Some people use it. But these are the basic things that are used in snarks and starks to move from a formula to gates, because snarks and starks only know about gates. Now, 2 super important tricks I want to mention. One thing which I omitted was subtraction, right? Let's say you have the formula x minus y. Well, this one is actually easy because you can represent it as x plus minus 1 multiplied by y. So you don't have subtraction anymore, you have multiplication by minus 1. So that's how you go with subtraction. If you have in your formula, if your algorithm have subtraction, you just represent it as minus 1 multiplied by y. And the more subtle trick is division. Let's say in our formula, we also had some other parameter d, and we actually had to divide by d. How you do division? We never discussed this. It turns out, let's say I'm a king and the treasurer wants to prove to me that that he calculated everything and the result is this. What the treasurer can do, it can multiply the formula by d. So this equality, I can multiply both sides by d. And so this equality is identical if I multiply by d, there's no d on the left side, and I get d on the right side. And now I have only multiplications. I have 2 and additions. Don't have division anymore. So I have 2 formulas on the left and the right, which only have multiplications. And I also leave it as a little bit of a harder exercise to our viewers if they want to show how to apply the trick division by 13 to the formula for division here. Basically, to the left and to the right side, and you make sure that the left and the right sides are the same. What you can do, you can actually subtract also the right side from the left, and you get 0 on the right. It's a little bit more of a complex formula. If some of our viewers want to do it, they can do it. If not, they can just believe that you can also handle division. So now we handle actually multiplication, division, addition, subtraction. Pretty much everything that a typical computer can do, and we are done. Essentially, we turn each and every formula into a polynomial, and we can use our trick. Okay, so now let me slowly reiterate what we achieved today. During the previous session, we discussed how one can take a simple mathematical formula, just addition and multiplication of prices and computing the total, and turn it into a provable computation by injecting this hidden law. Today, we discussed a more generic fact that any computation, any formula can also be injected into this hidden law and turned into a combination of additions and multiplications, something which is called arithmetization, right? So now we can take any computation, we can turn it into these additions and multiplications, and we can apply our hidden law. And our hidden law is not really so secure, but in the future sessions, we're going to discuss more secure hidden laws provided by PLONKs. The last thing which we didn't discuss yet, but it's important to discuss, and something that we omitted intentionally, is computer memory. If you have a computer, the computer doesn't simply compute a single formula. It actually computes multiple formulas and saves and reads data from memory. Even a simple calculator, like here on the right, has a memory button, so you can save a value and later recall this value, and this makes the calculator much more useful. But computers have many more memory cells than just a single cell that the calculator has. So in the next section, we're going to also discuss how we take memory and turn it into ZK? How we add memory into ZK? And so once we have the memory and computation, addition, multiplication, subtraction, division, we pretty much are going to have everything a typical computer has. And that's going to be the end of our description of the front end. How we take anything and everything and turn it into something in something which is being able we can handle using this hidden law. Then the next sections are going to be about the actual hidden law, and we're going to go into details of PLONK.
Awesome, great. So I didn't realize we're going to get a super cool in-depth math session today. And I get to see very old school calculators, which I have very fond memories of having to use. So arithmetization, that's this week's topic. You already know next week's topic. Look below, you can click subscribe. This is a whole series. The cool thing about Math for the Impatient is a whole series. And in fact, one of the things that Stan and I have talked about, and I need to probably do sooner rather than later, is actually start to combine them so it's one long video and people can just kind of watch as they like. But you can subscribe below. I think there's over 25 videos so far in the Math for the Impatient. This is the mini series on ZK. Stan, thanks again, and look forward to the next one.
Okay.
Bye.
Bye, Michael.